Okay, question 2. A register stores the binary number. So here's our binary number in its register. So a register is just a small memory location inside the CPU, and that might crop up in another question later on in this paper. Okay, part A. Give the denary number for the binary number stored in the register. Okay, so we're going to go denary to binary. So let's go ahead and put our powers of 2 table onto the binary number. 1, 2. Okay, and next we're going to add up the place values where we have a 1 digit. So we have got 128 plus 64 plus 32, no 16s, no 8s, no 4s, we've got a 2 and we've got a 1. So let's go ahead and do that. Okay, now we'll add these together. 128 plus 32, 160 plus 64, 224 plus 2 plus 1. That gives us 227. So that's our denary number. Let's go ahead and put that in the answer space they've given us, and then move on to part B. Give the hexadecimal number for the binary number stored in the register. So this time we're going from binary to hexadecimal. Now anytime you have binary and hexadecimal and you're doing a conversion between the two, so binary and hexadecimal, we only ever work in groups of 4 bits, or another name for a group of 4 bits, in nibbles. Okay, so any binary numbers will only be written in groups of 4. So let's split our number up into groups of 4. So starting from the least significant bit here on the right hand side, I'm going to write out that number. So we've got 1, 1, 0, 0, takes us up to here, and then we'll write our next group of 4, 0, 1, 1, 1, and then we're going to pop our table above each of those, and now we can work out what each of the values are for these 2 nibbles. So we've got 3 on that one and we've got 14 on this nibble. Now, as you will know, in hexadecimal we can only write a single digit for each nibble. So this one's okay, we've got a 3, but we can't write 14. So this is where we need to remember the conversions from denary to hexadecimal. So we know that 9 in denary is 9 in hexadecimal. Then we've got a few more numbers here, all the way up to 15. And so we're replacing 10 with a single digit. So from your lessons you'll know that we've got A is 10, B is 11, and so on. Now I would recommend that you write this on the question paper somewhere, simply so you can refer to it. I see quite a few mistakes where this first part has been done correctly, and then there's just been an error in this conversion because somebody's tried to do it on their fingers or in their mind. If you're 100% confident, fine, do it that way, but my top tip here is always just write this out. I've got 14 is E, so I can replace that. So we have E3. So let's go ahead and write our hexadecimal answer up in the answer space. Okay, moving on to C. A logical left shift of 2 places is performed on the binary number stored in the register. Now, the importance of reading the questions twice can't be emphasised more than on this one. I see a lot of candidates who see a logical left shift, they go ahead and shift it 1 place, think they're done, whereas actually if they'd have just read the question a second time, they'd have noticed it says 2 places. Okay, so the way I would approach this, so because we're doing a left shift, we're going that way. So what I'm going to do is I'm actually going to move, so there's the first digit in this register, the second digit will be here. I'm actually going to start writing it in this one and then going from right to left. So the first digit coming back across here is a 1, so I'm going to write my 1, and then I'm just going to move, filling in the other digits as we go along. Okay, Now the last two ones won't fit, but that's fine, I don't need to worry about those for this question. You won't get any marks unless every bit in this register has a digit, so we need to fill in anything that doesn't have a digit with zeros, and that's our answer for that one. Okay, moving along. D, the negative number minus 99 needs to be stored in the register. Complete the register, so they've given us a register down here, to show the binary number that would be stored. Using 2's complement, show while you're working. So 2's complement is a method that we use to convert a positive number into a negative number, into its negative binary representation. And we simply have the binary number, flip the bits, or invert the bits, and then add 1. Excuse me. So let's have a go at that. Right, so we've got minus 99. So first thing we need to do is we need to turn that into its binary equivalent. So let's draw out a table. Now it tells us, oh, it doesn't tell us, but the register has 8 bits. 8. So what I'm going to do is I'm going to do 8 place values. There's my 8 place values, and now I'm going to take my number 99, and let's go ahead and turn that into its binary equivalent. So I can't take 128 away from 99. I can take 64 away from 99, and that leaves me with 35. I'd always recommend writing down the remainders as you go along. It helps you to keep track of where you are. So I can take 32 away from 35. That leaves me with 3. I can't take 16 away from 3. I can't take 8 away from 3. I can't take 4 away from 3. I can take 2 away from 3. Leaves me with 1. And I can take 1 away from 1. And we're all done. There's our number. Now, that's our binary number initially. Now we need to go through the 2's complement process. So step 1, we flip the bits or invert the bits. And then step 2, we add 1. So 1 plus 0 is 1, and then we don't have anything else, so essentially we're left with the rest of the number. And that should be our answer, so let's pop that in the answer box. Okay, last part of this question, E. The number, this binary number is added to another binary number. Add the two 8-bit binary numbers using binary addition. Give your answer in binary, show while you're working. Okay, so there's 4 marks on offer here, so which is a nice amount of marks for something that's pretty straightforward. So we'll carefully write down the 2 binary numbers first of all. And then the second binary number. Okay, and now we'll perform the addition. So and with binary addition, there are just a few rules that you need to know, and again, if it helps, write them down on the side. So we need to know that 0 plus 0 is 0. We need to know 0 plus 1 is 1. We know that 1 plus 1, now 1 plus 1 is 2, but in binary we write 2 as 1, 0. So we have to answer, remember this is a binary addition, we have to answer in binary. And then the last rule you need is 1 plus 1 plus 1, so 1 plus 1 plus 1. Now we know that's 3, but in binary we represent that as 1, 1. And again, if it helps, write these down in the side of the question. So 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1, so that's 1, 0, so we pop a 0 down and we carry our 1 across. 1 plus 1 is 1, 0, so we put a 0 down. Now you can just write the 1 here, or you can carry it across, stick with your method, and then we just got that 1 in that column. Okay, so that's it for these questions. Let's have a quick look at the mark scheme. So straight answer for A, 227. Similarly, we've just got E3. So 1 mark for each correct character in the correct order. Something is just to come back to. I do see sometimes candidates, so for this one E3, for some reason swapping the numbers around, and I'm not quite sure why that happens, but just always keep the digits in the order that they're written when you've worked them out for your answers for those questions. But yes, I do see that. That looks right. Yeah, that's right. Okay, and then we've got 100, 1101. Yeah, so we've got the 2 marks here. So 1 mark for the working method, flip and add 1 mark for the correct answer. So if you got the answer wrong and they could see that you'd flipped the bits and tried to add 1, you'd get 1 mark for that. And then finally we've got our answer for this one. You can see that was a very easy binary addition actually for 4 marks. 1 mark for each correct nibble, maximum mark 2, 1 mark for correct working, e.g. Correct carry. So yeah, so make sure you have your workings on there. 1 mark for the showing of the overflow bit. So we've got this extra bit that didn't fit. Doesn't actually specify the answer must be in 8 bits or must fit into a register. So we just put the whole thing there. So right, okay, so that's that one. Hopefully that was helpful. Next video will be question 3. Thank you very much.